So this first lab, I'm going to talk about experiment tracking, which is something that's very near and dear to my heart. So I'm one of the co-founders of Weights and Biases. And prior to starting Weights and Biases, I founded a company called, today it's called Figure 8, that did data labeling. So I've been really close to machine learning now for nearly 13 years and care about it deeply and think all of you are like super cool. And I want to help you. So we're going to be talking about the tool that we have today and how it can help to manage various experiments. So in this first lab, we're also going to talk about running experiments in parallel. So Sergey was talking a lot about kind of infrastructure and data parallelism, and we're going to actually do it in the lab today, which should be a lot of fun. So the goal of this first lab is just to get some familiarity with the weights and biases tracking tool. But I think the concepts here kind of apply to any experiment tracking tool that you'll find, as well as running experiments in parallel. So in terms of our kind of big picture, full stack deep learning experience, we're really just focusing on model training here. So before I dive into this, I wanted to talk about kind of high level, how we think about the weights and biases tool and kind of where it sits. So weights and biases, we were founded in 2017. We're based here in San Francisco. We've got 20 folks on the team, most of which are engineers. And these are just a few of our customers that are now using the tool within their organization. So OpenAI was a really early customer. It's been awesome to essentially sign up for like a denial of service attack whenever they launch a big distributed compute job. And it's actually how we originally met Josh. So it's been fun working with those guys. So at the highest level, what we're focusing on at Weights and Biases are really three key areas. So one is just automated experiment tracking. And with this, I mean, no more spreadsheets. We're just going to, for you, keep track of everything that you tried and store it in a central database so you can always go back and see what the heck happened. We also try to do a bunch of clever things behind the scenes to ensure that you can reproduce that result. I'm sure everyone here, you always commit your code before you run an experiment, right? So I mean, it's like little details like that we thought about, and I'll show you later, that will store some information about that so that you can get back to the original state of your experiment. The second key area is really sharing findings with the team. So especially as these companies are growing out a machine learning function, or if you're just working with others, it's very difficult to say, share even a TensorBoard instance, right? So we've created the tool to really have sharing and collaborating as a core set of functionality. And I'll be showing you some of those features as well. And then ultimately, we want this tool to, in as lightweight way as possible, and kind of going back to Sergey's slides, we're very much a point solution. So we're trying not to be terribly opinionated. And we're trying to work with kind of everyone in the ecosystem so that we can play nicely with them. But ultimately, our mission is to make you guys more productive and your models better. So we provide a number of debugging and visualization tools to really help you understand what's going on under the hood. So before I get into the actual weights and biases tool, I just wanted to like geek out with you guys for a little bit, because this is also something near and dear to my heart, the Jupyter Hub instance, which I put my DevOps gloves on and set this up. So Jupyter Hub is running inside of Google Cloud. It's running in Kubernetes. And we basically provision these Docker instances when you signed up and enter your code. And then this allows you to have a GPU in a cloud-based environment. So if we type NVIDIA SMI, we'll see that we actually have 2 cutting-edge Tesla K80s. So I wanted to show you just a couple like nerdy things about the hub for those that might want to mess with it. One, yeah, it's got a dark mode. That's right. Two, there was some talk of VSCode, and this was like my ridiculous project last weekend for reasons that still aren't really clear to me. I just think it's super cool. VSCode actually has a hosted version of it. Like you can run it on a server. So if you go to File, New Launcher, you can actually get an instance of VSCode, which will just open up in a new window. And now you're in VSCode on the GPU. So instead of doing that like file syncing thing, this is just like serving up the interface from that Docker container inside the Kubernetes cluster. And you can get, you can use the extension manager to ensure you install like the Python extension or anything else, and then you'll have access to this. VS Code doesn't have light mode, I don't think. It's only dark mode. But yeah, for folks who want to play with this, I encourage you to. Be warned, it's like alpha. I haven't really tried it. I did it last weekend, so. Cool. So one last bit of information about the hub. Some folks asked in Slack, how long do we get access to this? The code you entered in this morning gives you access for 30 days. So the easiest way to get to this is just to go to hub2.wnb.us, and that will bring you into this instance. We provision you 20 gigabytes of storage. The way the hub works is so that I don't rack up a massive GPU bill. The hub shuts down when it hasn't heard from your web browser for 60 minutes. So if you guys want to do like training overnight tonight, you've got to plug in your laptop and leave your browser open. We pre-provisioned a whole bunch of GPUs for this class. After the class ends, we'll kind of scale down the cluster, which just means when you guys come, we'll have to spin up a new machine. And that takes like 10 minutes for a number of reasons. But there's the high-level overview of the hub. Cool. So let's dive into the lab itself. So this first lab, we're going to be in FSDL Text Recognizer Lab 3. And if we just open the README file, we'll see some information about what we're going to be doing today. So number one, there's this like let's get started with WNB, which gives you some instructions. We don't have to run any of these instructions because I created the hub and I just did this for you already. I logged you guys in. Your credentials are inside of the hub. You're all good to go. But if you wanted to use weights and biases from your own machine or your own environment, you would likely want to follow these instructions, or at least run WNB login to get your API key onto whatever machine you're working on. So let's go ahead and just run our first weights and biases experiment, and then I'll walk through the code as to what gave us these things. So we've got our tasks, train character predictor. So this is going to go back to that first lab where we're just classifying individual characters. And in lab 3 here, we've now instrumented this with weights and biases so we can see what we get by running this. So I'll just run we get all these delightful deprecation warnings. Cool. Now you'll notice there's some new output here from the previous experiment. So first we see that we're syncing run good totem 136. So weights and biases is going to assign a unique name to your experiment unless you assign one yourself, which I'll talk about in a bit. But we try to make really nice, fun names. So hopefully we see some other good ones today. And then we have 2 links. So we've specifically configured this Git repo to have a project named FSDL Text Recognizer November 2019. So we're all going to be posting experiments to the same project. Question?
Can you make the font bigger?
You bet. Is that better? Cool. So we have a link to a project, which is going to contain all of our experiments. And then we have a link to an individual experiment or a run in this as well. So we can copy this link to the run and open it up in our web browser. And we'll see this interface. So it's training live. The metrics are still streaming in. What we're seeing here is that we're going about 10 epochs. And I've created a shared plot up here that's showing our loss and our validation loss. And good news, we're not overfitting. Cool. So here we can see kind of all the metrics that are logged. In this case, it's just grabbing any metrics that Keras was tracking and logging them for us. So we have accuracy, validation loss, validation loss, and a really useful plot, epoch. So the cool thing about this epoch plot is if it just so happens our default step and epoch are the same in this case, but any metrics that you log that are just increasing forever, you can use that as an x-axis. So we're using kind of our default step, but you could use epoch here as a default step if you were logging multiple x-axes. So the first thing I want to call out is all the information we got because we instrumented our code with W&B, and then I'll show you how we actually instrumented it. So number one, we're running within a Git repository, so it noted that fact and said this was the Git repo we were running in. It also noted the exact commit SHA that the code was at. So we know the exact state of the Git repo. And then here it also noted the actual command that we ran to run this experiment. So I should be able to reproduce this result. We also have these two bits of information. So config, these are all the hyperparameters. So these are literally that nice JSON config object that's been configured here. But now we're storing that right alongside this experiment, so we know exactly what settings were used to get this experiment to run. And then summary is just the most recent value of any of our performance metrics. So it's kind of the final epoch value of metrics. So kind of a nice thing that you get for free are these system metrics. So here we can see we're really not using much CPU at all. We are using GPU, but only 35% of it. So maybe we could increase our batch size and use more of that GPU. You also see that we're increasing the temperature of our GPU, which seems good. That seems to be something we want to do. One other thing we capture for you is essentially the model.summary. So in your terminal, when you see kind of all the layers and how the network is laid out, we capture that for you here in this nice graph. On the left, we kind of see the way the data is going to move through the compute graph. And in this case, it's a simple sequential model, so it's just one straight line. But we'll see some more complex examples later. The other thing we do is we actually stream the terminal output itself. So if you're running this overnight and you go out tonight, maybe, dinner, but you got to check to see if it's still running, you can use your cell phone and get a nice view of the actual run itself. And then an important piece of weights and biases is what we call the artifact store. So we're going to store a bunch of artifacts that we think are important automatically for you. Like one being a requirements.txt that has the exact versions of all the Python libraries that were in this environment. Another being a diff.patch, which will show me exactly if I made any changes and I didn't commit them. Now I've actually got a patch file that I can apply to get to the exact state of the code. You can store your own artifacts here. Or even better, with our Keras callback, we're automatically storing the model. So now here we've stored the best model for this experiment, and that's in this H5 file, which we can download from the web interface, or show you in a bit. We have kind of Python APIs to access all of this information as well. So let me show you the code So if we look in lab 3, inside of training, the first piece of code I'll show is the run experiment. So if we're using WNB, you need to import WNB. So WNB is a Python library. It's actually open source. All of the source code for WNB that captures all this information, it's freely available on GitHub. Our backend, where we're seeing these metrics, that's something that we're hosting. But we also provide that backend as something you can host inside of your own network or AWS account. The source code for that is closed, but we allow you to kind of self-host the weights and biases experience as well. So I import WNB, and then inside my experiment, we say if use WNB, we call WNB init config equals experiment config. So WNB init is really the only required call to instrument your code. If you're already using TensorBoard to store metrics, you can add a keyword argument that says sync_TensorBoard equals true to WNB init, and then we'll just mirror everything that's going to TensorBoard to weights and biases as well. And as a bonus, we'll spin up TensorBoard for you in the weights and biases interface so that you don't have to manage TensorBoard. But since we're not using TensorBoard, we need to also kind of log some metrics. So one way to log metrics is just calling WNB.log, which is kind of the core foundational API of weights and biases. So if you're running like a PITorch model and you write your own training loop, you would essentially call WNB.init and pass in whatever your hyperparameters were, or any inputs that might impact the final performance of your model. And then you're going to want to call WNB.log every in batches. In our case, we're calling it once every epoch, but that's really up to you. So this WNB.log is actually just getting called once per run, and it's getting called after the model has been fit. And we're just storing a single metric called test metric here. So to see where the real magic is happening, that's in util. So here in util, we're importing WNB. We import the WNB callback. So this is a Keras callback that will just introspect Keras and do a whole bunch of nice stuff for us. All we got to do is add it to the callback list. And then I also wrote a custom callback.
There's probably going to be a question. What other frameworks do you support?
All of them. Yeah, as I mentioned earlier, we're really trying to be kind of the Switzerland of ML tools. So we're trying to play nice with anything that we're seeing people actually use in the marketplace. So in terms of frameworks, the frameworks that we have kind of first-class support for are PITorch, Keras, TensorFlow, FastAI, XGBoost, and Scikit. But ultimately, we have support for like anything written in Python if you just use our really low-level APIs. These are just wrappers that make the experience with these frameworks nicer. And then we have integrations with a lot of the tools that Sergey was talking about earlier. So we kind of play nicely with SageMaker. TensorBoard, I mentioned, we can just sync and run for you. Kubeflow, we do some nice things if you're running training in there and kind of automatically extract some metadata. We're working on an integration with MLflow. So MLflow tackles more than what weights and biases tackles. Kind of the tracking component is one small piece of MLflow, and they have kind of a whole kind of data pipelining and also model deployment piece that we're not currently tackling. So you could use us kind of alongside MLflow if you want some of our richer comparison UIs or tools like that. So kind of going back to the documentation, one of the more powerful things about the weights and biases tool is the ability to log more than just scalar metrics. So in your call to WNB.log, of course you can log just arbitrary scalars, but we also let you log rich media. So if you're generating a matplotlib or a plotly plot, or you have some like images that you want to log if you're doing a computer vision problem, maybe you have video if you're doing like RL and you want to show the simulated environment, audio, text or tables for NLP, you can log how the model is literally performing as the model's training, and then we can provide nice UIs to give you a sense for if it's actually doing what you hope it's doing. outside of these higher level aggregate metrics. So that's what this WB image logger is doing. So what I wanted to do was to be able to actually take an image from whatever data set I'm working with and run inference on it, and then display the results in WB in some nice way. So because Sergey and Josh organized the code base in such a way that there's this really nice model wrapper that provides a predict on image method, I can now use this callback kind of regardless of the model. As long as that model can predict on an image, this callback will now, at the end of the epoch, essentially by default take 4 images from my validation set and grab the predictions and then log these WB.image objects, which will allow us to actually see what the model's doing in the UI. So that's not especially exciting with this character recognizer, because I didn't shuffle the data set, so I'm logging 4 zeros. But this will get more interesting when we're actually training on the lines data set. Cool. So there's my callback. Here again, if we use WB, then first I'm going to instantiate my custom callback that's going to log some images from my network. Next, I'm going to instantiate the default callback, which is going to log all of the metrics associated with the network, as well as save the best model and record the actual compute graph so we can see that in the UI. And then I just append those to the fit function, and we fit, and now the model's fully instrumented with weights and biases. That's all that had to be done. Cool. So I'm going to stop there. I kind of rambled on for a bit and see if there's any questions on kind of this simplistic individual experiment view of weights and biases and experiment tracking before we dive into multiple experiments and hyperparameter sweeps.
In case I want to run this in my on-premise setup, I can use that?
Yeah, so we have a VM, essentially. So if you're running in AWS, we give you an AMI. If you're running in GCP, we give you a Google Cloud image. If you're running on-prem, we can give you a VMware or other image that would then contain all of the backends and UI that's kind of on top of this.
Wonderful. Thank you.
Cool. So let's dive into actually making use of both of those.
There's a quick question.
Yeah.
How good is the support for PITorch?
Like,
is it as good as what you showed?
That's a tough comparison to make. So we have first-class support for PITorch in that we'll automatically hook into the model, and we can log the distribution of gradients or weights at any given layer within your network. The challenge with PITorch is there's no clearly defined way to kind of have a training loop. So by default with PITorch, you're always defining your own loop, which means we can't just have a nice callback that automatically grabs all these metrics. It just means that you're going to have to call wb.log manually inside of that loop, likely wherever you're printing to the terminal anyway, which makes the integration a little less magical, but I would say it's fully supported in terms of various versions and what you can log with it. There's actually, I just learned about a project called Poutine, which is a Keras-like wrapper on top of PITorch. And of course, FastAI, we've got first-class hooks for, which essentially is just running PITorch.
So I've actually tried to, I am currently using 1B with PITorch, and the one thing I found was that the graph visualization is not, I mean, it doesn't actually tell you how the layers are connected, it just gives you the structure of the model.
This visualization here?
The actual graph, yeah.
And you're saying the thing on the left isn't properly telling you the graph, or?
Yeah, it doesn't actually tell you the graph, it just tells you the model.
Oh, it's just one line, and you're not seeing all of the sub-modules?
No, like in PITorch, it's object-oriented, right? So you have models, and then you have sub-models and all that.
Yeah.
But it doesn't but that structure doesn't tell you how they are chained together, in what order. So that information is missing. Plus, when I run it on 8 GPUs in parallel, I get 8 copies of that in my 1D visualization. But with Keras, it's pretty good, actually.
Yeah, so currently with this graph and PITorch, it won't work well with nested models. So with PITorch, if you just have a single model that has all of the layers tied into it, it should work as well as Keras. If there are nested models, we're currently not walking that tree, which is likely what you're seeing. But that pains me, and I want to walk the tree for you. So. Mm-hmm.
So what I'm feeling that if I want to visualize any specific type of prediction, for example, detection versus segmentation versus semantic segmentation versus instance segmentation, so I just have to write the custom callback, and that should work.
I mean, as long as you can generate an image, that image can be logged. If you wanted to be able to have the layers, say, apart from each other, so the segmentation mask and then the original image, we do have support where you can log those as separate images, and then we can help like overlay them and change opacity. But those are slightly more advanced features.
Okay, thank you.
Cool. So let's run some more code. So in the README, we're going to talk about running on multiple GPUs. So Sergey and Josh's script actually accepts the GPU argument, and that is an index into the specific GPU you want to use. So by default, that's 0. So here, if we just copy this code, and then from the Lab 3 terminal, run it, now, if I open a new terminal, I see that only my first GPU is being used, whereas GPU 0 is chilling. Cool. So now we're able to specify which GPU we can use, which is good. The next step in this is, well, how do we run kind of multiple experiments in parallel? And Sergey and Josh were nice enough to make this super easy through a couple helper scripts. So the first one is this prepare experiments script, which all this is going to do is read in a JSON file and then print out a number of commands, kind of an arbitrary set of commands that you might want to run. And then we have this GPU manager. Basically, what the GPU manager is going to do is if we say, hey, dash GPU equals -1, that's basically saying you pick out the GPU for me. So GPU manager is kind of querying the OS and saying which GPU is free, if any, and I'll pick either 1 or 2. So that way we don't have to manually choose 1 and 2 and manage all of this stuff. So here, if we go back to our terminal, if we run Python training GPU manager, I'm sorry, prepare experiments will show us something interesting. Oh, prepare experiments, and then it's training examples or experiments sample.json. So if you go inside of experiments sample.json, you can see there's this JSON defining 3 different experiments. So we're training 2 character models on the MLP dataset and 1 on the LaNet network architecture. So if we go back to the README, we can see that there's this nice tool And this task prepare sample experiments did what I just did manually. It's just calling to generate those 3 lines. What this is going to do is it's going to pipe those 3 lines into this program called parallel, which will just run however many of those commands in parallel. So we're saying we've got 2 GPUs in this box. So we're saying let's run it in parallel with the -J2. So we're not going to see output here. But if we go back to the weights and biases UI, we can see that we've got a whole bunch of experiments running. So in this UI, now we're seeing experiments across this entire classroom. So anyone running on their laptops are going to see experiments here. So we could see Bshen, Tom FSDL, FSDL Catch-22, and more folks coming. If you want to see just your own, you can hit this filter button, and then you can say, show only my work. So now these are all of my experiments. I can expand this table out, and then I'll see all of the various metadata we have about the experiments. So here we've got all of the hyperparameters as columns, such as window stride, window width, batch size, which data set we were actually training on, as well as all the performance metrics. So we've got a bunch of these like noisy columns here. If I hit this magic wand, it'll reduce to just columns that have some changes in them. And here, any of these columns you can pin. So you can say, OK, I want to pin this column. That'll mean it always shows up on the side. And now when I collapse, I can see kind of my important metrics right alongside all of the visuals. So let's pop into one of these that's running. One other nice thing is that while it's running, you can actually stop your run from the web UI, which I'm not going to be nasty and stop this run right now. This is a public project, so all of you can post data to it. And in like real world use cases, you'd set up likely a private project or a project for your team within the organization. The way that we define kind of what project or where to send this data to is through this WB settings file. So we created this WB settings file that has entity, which is FSDL, which is a team that we created for this class. But entity could also be your username. So if you wanted to post experiments just to your personal account, you would change the FSDL to your entity to your own username. And then project is essentially just a bucket, much like a GitHub repo has a name. Weights and biases project is some group of experiments. So you could customize this for yourself as well and change it in this settings file. Both entity and project are also overridable in your call to WB init. So those are arguments you could pass here. So if you want to say entity equals my username or project equals whatever, those could be set in this interface. Cool. So I'll stop there and pause for questions before we dive into hyperparameter sweeps. How do you set the URL?
Yes, you mentioned the entity name and the
Yeah, so whatever entity is set either in your settings file, which is in this WB settings file relative to wherever you're running the command, or you can see like here, entity is FSDL and project is FSDL recognizer. So that's exactly what's in the URL for this. You can also set that in your call to wb.init. So here I could say entity equals Van Pelt to have it post to my username. And then that URL would have Van Pelt instead of FSDO.
Even if that's running locally on your system.
Yeah, so you can specify an environment variable called WNB mode. WNB underscore mode equals dry run will mean that it will just store metrics locally and not post them to the cloud. You can then later sync those to the cloud or to your own installation of weights and biases. The way we do it is we actually create these run directories and store metadata in it. So you can see here we've got all of the metadata that was collected by the weights and biases tool actually in a local directory on your system. And then we have a command line tool, WNB, that would allow you to sync a given directory. So if for some reason you needed to train without internet, you could do it this way and then sync the data later. There's also a WNB restore command, which I think we mentioned in the README. Which allows you to specify a run path. So that run path is this guy right here, which is kind of entity, project, and then run ID. And if you just copy that, then you could say WNB restore, and it'll actually check out the code to whatever the state of the code was when you ran it, apply the diff, pull down any metadata. Mm-hmm.
As far as CI workflow goes, would you recommend pulling models from WNB into whatever CI situation? Or is there a different workflow that you would recommend and not use the models that WNB is storing?
Yeah, so I mean, I think this repo itself is like an interesting answer to that question. We kind of have two different storage modes here, and I'm sure we'll be talking about this more. But one is using Git LFS, which is the large file store, and the other is our kind of cloud storage syncing. We can work in either way, so it's really up to you. We currently, our API is polling based. So if you're connecting us with CI, you can essentially query for any runs or set of runs to compare and then trigger actions. So you could say, if I train my model and it gets past some baseline, then trigger something to happen inside of CI. That happens as a result of kind of querying our API. We expect to have kind of push notifications or webhooks in a new release in the next few months.
Yeah, we actually, I think we made our own little script that looks for the best metric among all the runs within a tag, and then like downloads that one in CI. Because the WNB has an API, so all of your runs you can query via the API, and then you can do stuff with that. We should probably move on.
Great.